to MTVTA, guys. I'm your guys' host, Trent Manager. All my new viewers, welcome. All my returning viewers, of course, welcome. Really glad to have you guys back here. So I want to bring you guys a quick video today going over the 5 blockchain interview questions and answers, part 1. This will be one of a part 2 series as we go through some critical and some basic questions that need to be asked in your blockchain interview, or just overall a student, or you're looking to get into the space as well, or just overall looking for a challenge or something new that you may not have known beforehand. So my name is Trent Manager. I'm a Hyperledger and blockchain developer currently. Been one for about a year and 3 months now. Continuing to document my educational learning journey through free readings, free coding tutorials, along with live streams in my Patreon class. This is how I'm navigating myself through the ecosystem. Moving forward, this is our Getting Started tab for our glossary for our questions. These are going to be the 5 questions that we will be covering today in this video. Take a look now. If you don't know the answers to any of these, or maybe you do, just hang tight and we will be going over these shortly. You can write down your answers now on a piece of paper, or just pause the video here and give an idea as to what you think the answers are. Establishing the differences between Hyperledger, as blockchain and Hyperledger share some very similar similarities, but also do differ in some instances. Hyperledger is a platform organized for allowing enterprises to build private blockchains for practices. This caters to big supply chains such as IBM, Boeing, NVIDIA, AMD, 3M, and much larger enterprises. Hyperledger private blockchain is where you access the blockchain data is limited to predefined users. So something such as MSP, as we like to call it in the Hyperledger world. MSP is a membership service provider that gives a checklist of an identity of an individual who is either given a role, such as an admin, a peer, or a binary node. And from there, they have certain access and limitations on the network to what they can do. Bringing up question 1, Hyperledger is going to benefit an enterprise much better than it is going to benefit a small business. So most enterprises are going to lean toward the Hyperledger side, given the points that we have covered. Is a Merkle tree. Take a couple seconds for this before we do move forward. Covering a Merkle tree. A Merkle tree is a data structure which is used for verifying blocks. It is a form of binary tree which is containing cryptographic hashes. So I labeled here with arrows by color. So arrow 1 is going to be our one each leaf node and our hash of the block transaction data. Arrow 2 is going to be each non-leaf node is a hash of itself. From arrow 1, each leaf node is a hash of a block of transaction data. Each non-leaf node is a hash of itself with the prior node. Merkle root or hash root is the final hash of all the transaction hashes. So I know that seems a bit confusing, and one of our questions is going to give more in depth when we get into the block structure, but now let's break down the Merkle tree. So we see our L1 through L4s. So you can see here as to L1 and L2 catering to this branch, and L3 and L4 are going to cater to hash 1. So I labeled these by color, so let's break this down. So L1 and L2 are going to form into hash 0-0 along with hash 0-1. Equivalently, these hashes will come together from the previous block to verify that the blocks are in order. The chain, of course, does not go out of order, as that is the term of blockchain. Going into hash 0 as hash 0 and 1 combined into hash 0, as you can see on the screen. Therefore, taking the previous data from the block in order to the previous block that we have now, forming into the hash that we have at the top here. And then finally, going to the top hash with the blue arrow. For the construction, you can see how it all falls in one from L1 and L2, following L3 and L4. We have seen that we have the top hash, which caters our hash 0 and also our hash 1. The main meaning of this Merkle tree is a great way for defining hash functions and keeping the structure of the blockchain in order. Like I mentioned earlier, our next question, question 3, will go over the identification of a block. And this will, of course, tie in to one-to-one as to how the Merkle tree comes into effect. Can you identify a block? Every block consists of 4 fields. So we're going to start from the bottom here. Answer 1, which we have at the previous side, and the best way to think about it is a 3D block, and each side panel dedicates to a specific number, as I have here for previous hash, transaction data, notes, and hash as well. So let's start with answer 1. So hash of the previous block is stored on this side. So it holds the hash of the value of the previous block, like we talked about in the Merkle tree, to ensure that the chain is in course, of course, going in the right order. Going over to answer 2, contains detail of several transactions and transaction data. So the transaction data can be the signature, that can be as well the address wallet, and as well containing several other pieces of security and other protocol layers. Going over to 3, nonce. Nonce is a random value which is used to vary the value of the hash. So for example, this may be a little bit confusing, but let's just break it down into wallet terms. So you have your MetaMask wallet, you are sending 1 Bitcoin to a friend. Let's say that friend's name is John. And that friend's name is John is going to, of course, receive that Bitcoin, but in the numerical order that it was received. So let's say previously you had made some transactions and you have 3 in front of them. So your nonce would be 4, as the block has to be in order of how it was received. So you sent the 3 transactions before the 1 Bitcoin. Therefore, it has to execute those 3 transactions before giving the nonce approval of that 4th hash. Hash is an alpha numerical value which is used to identify a block. And also for part 2, the hash is an address to the unique identification of a block. It is a hex value of the 64 characters that has both letters and digits and is obtained by the SHA-256 algorithm. So let's break that down a bit as well. So when we have hash, this is the identifier or the transaction ID that you can see and verify on the blockchain. So sending from one wallet to another is broadcasted to the network for everybody publicly to look and see what is going on. So when this does happen, nobody does know the identity of the wallet receiver or the wallet sender, but they do see that the blocks are in order, that they are true, they are not tampered with, and that they are 100% transparent. And now going down to the SHA-256 algorithm as to how that is processed and generated into the hash, that is something that we will cover into our next question. And the SHA-256 algorithm is specifically bended to blockchains for producing transaction IDs for verification, as we are most familiar with blockchain regarding to Bitcoin, and the Bitcoin SHA-256 algorithm is applied to Bitcoin and Bitcoin only. This visual representation is helpful for me as I'm a big visual learner, as I know most of you guys are too, and if not, that's exactly why I do add a text version as well. Cryptography, and what role does it play inside the blockchain? So blockchain uses cryptography to secure its identities and ensure transactions are done safely with the hash function. Cryptography, in these 3 bullet points, is used for public and private keys, which are encrypted by decrypted data. In blockchain networks, public keys can be shared with all Bitcoin users. Private keys are kept secret by the user. Input data is connected to cryptography, along with the private keys being sent out to the user for a one-time use and one-time view only, sometimes more. The public key being retrieved back onto the public blockchain or the open source ledger to cryptography for the input data. So this may sound a little bit confusing, so let's actually break this down a little bit further. So private keys, we know, or secret phrases, are the one-time access key that are backed up when signing up or making a new wallet. This 24 secret word phrase or number or whatever it may be, or depending on the platform, is the only way to recover an account in case the password is lost. If the secret phrase is lost, whether it be a wrong capital letter, a word out of order, or simply a punctuation that is not supposed to be there as well, it will render incorrect. This security is some of the top security that we have in the blockchain space, and actually currently the world. A statistic I saw was you have about 85 times to win the lottery in your lifetime before you crack a secret phrase or a private key for cryptography and its role inside blockchain. So let's cover this back. Cryptography uses public and private keys to encrypt the data for the transaction hash, and what we covered in our previous slides as well, the data, the user and sender, as along with secret phrases as well. In the blockchain network, public keys can be shared with all Bitcoin users. Moving on to the second part of our question 4, to give a little bit better background as to how the SHA interacts with public, private cryptography keys and input data. That's exactly what we're going to do here. So the hashing function, blockchain uses cryptography to secure the identities and ensure transactions are done safely with the hash function. Taking these arrows here, we have secure, hashing, in the algorithm. Hash function takes in output data and returns the alphanumerical output of a 64 characters, and that's what we get in our string of transaction data. And SHA-256 stands for the number of bits it takes up on memory for that algorithm. So just a little background information as SHA-256, how it operates, what it does, and why it's important. That you would state is the Pragma Solidity version. So there are two ways that you can state this depending on the environment that you're running in: Ganache, Truffle, Solidity IDE Remix, or any other open source software that you're using to test your smart contracts. It is necessary to specify the version of the Solidity at the beginning of the code file ending with .sol, as it eliminates the incompatibility errors which can arise while compiling with another version. So this is going to define our Solidity version as to what we are going to compile our contract with. So this is what you would write: Pragma Solidity 0.4.17 or Pragma Solidity equals 0.5.0 or 0.60 encased. Something to consider in terms of security protocols, overall patches and bugs for deployment, and also Web 3.0 injection, and along with any other connection from API keys or anything that needs to pull any external data. The compiler version can and will give you errors if things are not set up correctly. So it's very important to choose the right version. In my conclusion here, I wanted to wrap up and say thank you guys so much for sticking to this video, and I hope you guys learned something new and you enjoyed the information that was shared. I will leave specific links for my academy and teachings down below, sharing this with friends or family, any coworkers that you believe may value from this information. As well, we will have a second part series coming out with 5 more questions that hopefully can either brief your knowledge on the current topic, or of course help you in any interviews or any sort of business ventures that you were expecting. Thank you guys so much for tuning in today. I will link all my socials below if you guys want to give me a follow on social media, and of course check out my Patreon Academy, where we do teach free coding tutorials, technical analysis updates, live streams every Tuesday, Thursday, and much more. Thank you guys so much. I will see you guys in the next one. Bye-bye.